for Lauro Rossi. So you see that we have different perspectives, and we will have another one completely different again. That's the interesting is to put together a different perspective from my side. I don't know if everybody agrees or not. It's quite interesting. So Lauro is an environmental engineer with 20 years of experience in disaster risk reduction at national and international level, with special focus on flood risk assessment and early warning. He works for the CIMA Research Foundation as early warning system program director. He coordinates the CIMA innovation, development, and implementation of early warning system in different contexts and for different hazards, mainly floods and drought.
So thank you very much for this invitation, Jerry. It's going to be hard to talk about quantitative approach in risk assessment and early warning after this, let's say, beautiful introduction from my colleagues. But I think this is a very good exercise that Jerry put together, try to gather different and very different perspectives about risk assessment. So I'll try to, and I was required to speak about numbers and quantitative approach. So I hope you bear this presentation. Okay, so a few words about the CIMA Research Foundation. CIMA Research Foundations, for those of you that don't know this organization, was founded in 2007 as part of the civil protection system in Italy. And we are mandated to advise the civil protection in Italy for floods and forest fire by law. Of course, we keep on working in Italy, but we extended a lot of work, let's say, worldwide, and we work together with development banks and the United Nations, the European Union, worldwide now. So, and today I'll try to talk about this nexus between the risk assessment and say very quantitative risk assessment and early warning, and how, I mean, these two methodologies that normally they work separately, they can be combined together better assessment of the impacts. This is, I mean, the classical definition of risk. You've seen this equation before. The capacity term in this side is contained in the vulnerability part. But, and I mean, let's say we can normally define this risk as the probability of harmful consequences associated to the impact that this hazard would cause if they occur. So methods for risk assessment, and talking here especially in economic terms. So the focus of this presentation will be exactly the quantification of what is measurable, not what is not measurable, as we have heard before, which is the economic losses, and then population affected, of course. So risk assessment based on historical events. This is, I mean, the first simple way to quantify losses. Actually, we just count losses that occur over a certain period of time, and from there we can, I mean, provide some average of these costs and try to these losses and try to estimate what is the average annual loss. Then, of course, is something appear. I mean, this is another event appears of this. One of those events is not quantified. I mean, the average and the statistical sample change a lot. The problem with this method is that it's not I mean, normally we don't have this series of continuous series in time of losses long enough to make any statistics. So we try now. Well, another method is to introduce scenario-based risk assessment based on the equation that we saw before, and see. I mean, based on, again, historical experience, we take one or two scenarios that we think that are relevant for now our analysis, and we focus on that scenarios. This is not a comprehensive approach, but it gives us some hint how to let's say prioritize your intervention. For example, we take the worst scenario, the most frequent scenario, or hypothetical catastrophic scenario that it hasn't happened yet, and we can, based on these studies and take those scenarios reference, we can take some mitigation measures, some adaptation measures, depending on what you're facing. And then we have what we call the probabilistic risk scenario, that we do what we saw for the scenario-based approach, but we, let's say, multiply the cases and try to have, let's say, different phenomenon, different hazard that are impacting exposure with a certain vulnerability that generates impacts, and then you count these impacts over time. Of course, this approach has to, let's say, has to be based on modeling facilities. And the idea is to not to, let's say, model 10 scenarios or 100 scenarios, but a large amount of scenarios that are ideally collectively associated and mutually exclusive, so that we have a complete statistics sample that, and from that we can derive, I mean, what we call the average annual loss, the maximum probable loss curve, or the exceeding probability curve. I mean, the probable maximum loss curve, the exceeding probability loss curve are more or less the same. They change the way they measure the probability. One is in written periods and the other in probability, but these are two metrics that are used to qualify this probabilistic risk assessment. So we need a modeling workflow or flag, and we start from the global circulation model into regional circulation model, then scale. Then we applied the hydrological and hydrodynamic models to get detailed hazard maps. We ran thousands and thousands of simulations of those events, try to keep this interspatial relationship between events, and then we add the impact part, exposure and vulnerability, and to measure the risk assessment in economics terms. So this part, because of this methodology, that we can take explicitly into account the uncertainty that is related to this process. And we have two types of uncertainty, you certainly know. One is the aleatory uncertainty. So how the phenomenon can, let's say, occur, and how different, how rare, how intense are those phenomena. And then the epistemic uncertainty also calls this also called the secondary uncertainty, that is related to the unknown of the pressure, I mean, the limit of the knowledge of each variable that we measure. So, and this is, I mean, I'm sorry for the equation. I promise not to put too much equation in this, but this is necessary. So we have, regarding this epistemic uncertainty, we have, I mean, the water level. We have, of course, the mean water level that we measure, but it can be a little bit higher, a little bit lower. So in the end, we have a distribution of water level. As well, we have a distribution around the impact function that relate the water level with the level of damage that we have. And we convolute all these probability with the integral of convolution, and where we get the final damage ratio for each asset, for each building that is exposed to, or each building or each, let's say, asset that is exposed to risk, where we get, let's say, the medium damage ratio, but we also have distribution for the distribution of this damage. Then, I mean, we count on, we have this for each asset, we put together in one scenario, and we repeat experiments for thousands and thousands of scenarios until we get this, this curve that relates the losses with probability. And once you have this curve is actually described, it's all that you get to dimension your mitigation measure in, let's say, economic term. You can, let's say, dimension your contingency fund, disaster risk reduction measure, risk transfer, mitigation measure. And this is how this can change due to the climate change and population increase, or reduce through mitigation measure and climate change adaptation. By the way, the integral under this curve gives the AAL, so the average annual losses. Let's put this into practice. We apply this methodology in 24 countries in Sub-Saharan Africa. We are on this country first for the World Bank. They were interested in economic losses. Then for the UN, there are more, let's say, support to the countries. It was already said, it was data scarce environment with medium to low level of technical expertise, institutional challenges, and as a challenge also to capacity development. But we learned that there are a large potential application for DRR, especially in those countries where disaster is very, very linked to economic development. Actually, our interface was mainly the disaster risk manager, but we work a lot with Ministry of Development, Rural Development, or Economic Development. Some of these results, those are the classification according to the Sendai framework. We talk, I mean, basically the impacts are direct economic losses of potentially affected population. And we try to differentiate the economic losses into different sectors. So for each country, we have this differentiation and this disaggregation. Some of the results here you can see the AL in current climate. For example, this is for Zambia, and projected climate condition, how they varies. This is an important, I would say, curious result for Angola, that we see that actually the AL stay the same for present climate and future climate condition, but the distribution of these losses varies a lot. If you put here, for example, for a return period of 100, so 1 in 100 year event, we see that for the same losses, we have a return period that this in present climate is 100 years, and in for future climate it's about 25 years. So it's really becoming much more frequent in the future. These are a kind of disaggregation. This is not social vulnerability. This is a kind of disaggregation of population affected by different, let's say, categories of population. We also take into account the population growth projection. And we also applied a kind of cellular automated model to model not just the population growth, but how this will be distributed around cities, taking into account the rural to cities movement and how these cities and center of aggregation can grow into the future. And these are some of the differences that we projected for suburbs of Luanda in Angola, for example, where we estimate a big increase of population. And again, I mean, this is another way to read this metrics. And here we have, instead of two curves, we have three curves. One is the present condition, one is the projecting condition with climate change, but with the current exposure, current population. But what if we take into account also population growth? And we have this huge difference between the curves. So the return period, an event that occurs 1 in 50 years, 1 in 50 years on average, it would affect 50 people in this case, 100 people, 100,000 people in this case, and 200,000 people in this case. So it's 4 times the present risk. So we develop all these kind of metrics and information. So how these can be used in for real-time impact assessment. Here we have an example in Zambia, Luapula, northeast of Zambia, March 2020. We have this information. This is the typical charter activation where we have detection from satellite, both optical and SAR satellite of the inundated area. But what about the economic impact? We don't have any information about that. How much is the province or the country going to lose because of this event? And how disruptive is this event in economic terms? I mean, for development of this country and these provinces, how rare is this event in terms of the impacts? So we look back at the risk profile that we have, and this is a real case. I mean, we are advising the government of Zambia in this case. And we look back in the risk profile that we have produced, I would say 1 year before, and the most similar scenario that we have computed and reproduced the event with flood depth, which is our hazard parameters, and we obtained this estimation of direct economic losses of $5 million US. So is this a disruptive event? Well, we could look in the PML curve. I mean, first of all, I mean, the quantification of this event with respect to social expenditure in Luapula province, and we see that this event alone, it taken more than, let's say, half of the budget of health sector public expenditure in Luapula in 2016. We didn't have measure of, I mean, this measure for 2020, but we can imagine that if money goes to recover this for this benefit, for this damage, they are not available anymore for improving the health sector. And then, is this an extreme event? And for this, we look at the PML curve, the developed provincial level, and we see that this event in that province can happen on average one in 15 years at provincial level. So I would say it's not extreme at all. It could be repeated. So this is how to link the early assessment with the background knowledge that we built for risk assessment before. Another, I mean, I'd say very local scale application here in Italy. So here, this is an event of Genoa. I think all of you remember the last big event in Genoa of 9 October 2014. We reproduced we reproduced the event both in Asam term, but also for this event we have, let's say, a special database of the damage that occurred there, and we could really calibrate the models. This is 1 meter DTN model, very, I mean, with a full set of hydraulic equation that mimic the propagation of water in the city. And we had this estimation of the impact. So we could really calibrate the model in a, let's say, quite a unique manner, because we have, I mean, those data sets were at disposal. So this is the current status of what actually happened, or what we simulate that happened. And so this model can also tell us, I mean, can be used in what if scenario. So what if mitigation measure will take place there? So culvert or diversion channel reconstruction could be, the diversion channel that is mapped here is not on the main course of the river, but it is on one of these major tributary, which is very small river. And so what we did, we actually, I mean, first scenario based, you know, I mean, what if there are those interventions? We reproduce the event, and you see it, I mean, the affected area is really left, and the damage would have been, let's say, 1/10 of the real damage. But then we compute the fully probabilistic risk assessment with this curve, and we see that, I mean, this is the current AAL with no intervention. We reconstruct the the loss exceeding probability curve for the intervention. And we see that, I mean, the extensive risk is practically eliminated. And we have this still intensive risk that is there, that causes this AAL, which is reduced, but I mean, it's still there. So what we get here is this benefit. So the economic benefit of only considering direct loss. No, this is, I mean, here, this is business continuity is not considered, all the indirect consequences not considered, but only considering the damage to asset, we have this benefit that we compare to the cost of the measure. And we see that this is really, really beneficial for that. And by the way, this is the decision that was taken then. So again, how we can take advantage of this procedure in real time. This is typical flash flood forecasting chain that we have implemented in our territory. I think it's more or less altogether. We have global circulation model that feed limited arid model. We had some downscaling process that gives different story of possible precipitation, and then discharge of forecast in terms of probability with this typical spaghetti plot. Okay, I mean, this is the current state. What if we can add here the impact part? Okay, this is again, a little bit more complicated on the atmospheric side, but let's focus on the impact parts. What if instead of having a statistic on discharge, we have a statistic of water level that we can then combine with exposure and volatility and have a statistics of impacts. So this is what we have now. So for example, you can see that there is a probability of overtopping. Sorry, this is probability chart that I think most of you are familiar with that probability chart, and say what are this is the discharge that is predicted, and you see that here, I mean, there is this probability of overtopping. Okay, but what about this? So what if an event is really overtopping, and what are the damages? We have no information about that part of the graph. But if we convert, I mean, these x-axis into economic losses and non-discharges, we have more or less, I mean, what we can compare in terms of economic losses, and compare these, for example, emergency fund that can be free to let's say help people and to help the reconstruction, or can be compared to different metrics, for example, the loss of a percentage of GDP of this city. In terms of population, again, I mean, this is what is the probability to have these people displaced because of this event, and the population to be evacuated at this amount with this certain probability, and we compare this, for example, shelter capacity, and how are those shelters able to host all these people or not? What is the population? So this is another, let's say, parameter that can add into the I mean, can inform your early warning system. I mean, this is just one slide about the non-linear transformation between stream flow to impacts. You see here that there is very little different between these two events of forecasted discharge that translate in big event, let's say big difference in terms of damages. And this is the other way around. Okay. No, what happened with the titles here? Well, anyway, to a very local time scale of the city of Genoa, we move now to the global flood risk assessment. This is an effort that we have been doing between 2011 to 2015 that brought to the global risk assessment. We are responsible for the United Nations of constructing this global flood model that was then published in 2015, where we covered 160 countries, model at 90 meters, 4 million flood scenario, I mean, floods scenario generated with PML curve and AAL. This is the global flood model that we produced. This is the average annual losses with exactly the same technique, but applied a very, very large scale, of course, with larger uncertainty again. This is the average annual losses related to capital stock. So with your capital stock that is exposed to risk, and this is a threat to the fiscal resilience, in terms that, I mean, your damage, your AAL can really put in danger your fiscal resilience. And this is the AAL compared to the social expenditure. So that can undermine the achievement of sustainable development goals. So. And again, at a global level, it was a study that, let's say, stopped at 2015. And now we have kind of, I would say, second edition, but with different actor. We work for the Coalition for Disaster Resilient Infrastructure. and United Nations Development Program. I mean, the focus here is not it's not only the complete capital stock, but it is the critical infrastructure. So we repeat actually the experiment, and for different hazard, we are responsible for the flood hazard, not for all the other hazard. So in a multiple sector that can be impacted, the critical infrastructure, power sector, transportation, water and wastewater, communication, oil and gas, education, health, and housing. But I mean, the methodology is conceptually the same. We have different thousand of scenarios that we combine. Every scenario give, let's say, an impact on critical infrastructure. That is measure. I mean, this is again the normal impact change that we see, but we have this part, which is the resilient index of the infrastructure, which is related to the functionality. So how the damage can really limit the function of that asset. So it's a slightly different approach. We try to condense in one index. So I think that all this global approach that can serve different initiatives. This is one initiative and the only one system that we have been involved for the last, I would say, 5-6 years. We are supporting 24/7 the ERCC. The ERCC is the European Response Coordination Center of the European Mechanism of Civil Protection. And we are, let's say, operational in 2 modes. One is the emergency mode that you can call anytime in 6 different hazards, and they will ask in 3 hours to complete a full multi-hazard report on a crisis situation that is happening or is going to happen in the future. And then we have in a routine operational mode where we provide 3 times a week multi-hazard report for the forecastable hazards, so that I can monitor the, let's say, evolution of potential crisis situation all around the world. Of course, the focus on European territory is much more, I would say, much more detailed, but we have to cover the entire planet. These are the activation of the last year. We had 37 emergency activation and around 300 multi-hazard routine monitoring report. The hazard that we cover here are earthquakes, tsunami, volcano, severe weather, floods, and forest fire. Chima is, I mean, the hazard chair, so the coordinator for the group of floods and the group of forest fire, the European. But this global, let's say, information that we put together can also serve continental and regional early warning systems. Here is another initiative that we have been developing together with the United Nations Disaster Risk Reduction and the African Union. So we are trying to build this coordination situational room at the continental level, here you see, that are in contact with regional situational room at ECOWAS, ECAS, ACMAD, SADC, and IGAD. They are exchanging information on regular basis, and they are producing this multi-hazard outlook twice a week at continental level. And whenever there is a red situation, the warning is communicated. Let's say there is an exchange of information with the national level, so that kind of assistant across the continent can be organized. This is the final goal. Yeah, sorry for that. Yeah, and I mean, for the IGAD region in particular, we have been focusing on flood early warning system. We have this early warning system at regional level. We have now in the final calibration validation phase. Not easy. I mean, modeling the Nile is not the easiest thing in the world for neonatologists, but we are getting there. And these are the impacts that we are producing through these modeling things of affected population that could be displaced, crop land affected, grazing land affected, livestock affected, roads, and loss of GDPs. Okay, we are at the end. I think you're still alive. Key messages. So the probabilistic risk assessment recognized as one of the most comprehensive and scientifically sound methodology to predict present and future losses, talking about economic losses in particular. They're able to produce informative economic metrics like AAL, PML, or exceeding probability curves to identify financial gaps, design strategy, and prioritize investment. And we see that also this huge amount of knowledge that we develop on probabilistic risk assessment can be brought into real time through the use of for the benefit, I would say, of early warning and early assessment, global, national, and local scale. So thank you very much, and I stop here and happy to receive your questions.